Hi, everybody. I'm Bryan Norcross along with Luke Doris. This is podcast number 11 of hurricane season 2021, and it's number 67 in our series. Welcome to September. Luke?
Halfway through the season, kinda.
Yeah, kinda, right. The peak is not quite here yet, but on the calendar, it's halfway through the season. So we're going to talk about Ida here in just a second because that was a big storm. And a lot of lessons are going to come out of Ida, and I think changes to the way things are done in Louisiana, at least, if not elsewhere in the country. So coming up on the podcast today, we're going to visit with Dr. Ronnie Avissar. He's the Dean of the Rosenstiel School of Marine and Atmospheric Science at the University of Miami, also known as Rasmus. Now, they're doing all kinds of fantastic research at Rasmus, including a hurricane forecast model and new ways of detecting how strong a hurricane is, and lots more. Plus, they use a helicopter to gather one-of-a-kind data for hurricane research. They really are doing some cutting-edge stuff there. And we'll talk about what it's like to be the dean of a top-level school like Rasmus. So that's coming up here in just a few minutes. Were you surprised how much was going on at Rasmus? It's like herding cats over there, it feels like.
Yeah, I knew that they had a lot, but after looking at what all he's in charge of, it's remarkable of everything that's going on there at Rasmus. So it'll be an interesting conversation.
It really is. All right, we're recording this podcast on Wednesday, September 1st, 2021. If you're listening at some point in the future for the latest weather, tune in to Channel 10, of course, in South Florida and Local 10 News, or local10.com, where every newscast is there live streaming. You can get it anywhere you are at any time. And the newscasts are on, seems like, most of the day. Also, the Max Tracker Hurricane app for the latest tropical information, and the Local 10 Weather Authority app for just your daily weather and the radar and like that. So get those on your cell phones. And you can go to local10.com/hurricane and sign up for a newsletter called From Bryan Norcross. Scroll down to the middle of the page, put in your email address, and we'll mail it to you. I write it just about every day. I mean, I don't know the last time I missed a day. Actually, the way the tropics have been going here for the last couple of years. But anyway, we mail it out, and also it's on local10.com. It's on Facebook. If you follow me on Twitter, you'll get a link to it there as well. So I put my thoughts together every day. Today I wrote Luke about Ida and the whole question of, was the hurricane forecast to hit New Orleans? The cone was kind of to the west of New Orleans, although they were in it. But the center line was to the west of New Orleans, and then the thing kind of jogged and made a little bit of a wobble to the right, so it put a bigger part of Ida over New Orleans. Anyway, Tulane University put out a tweet kind of saying that, implying that they weren't expecting that, and they were reacting to the idea that a strong part of the storm wasn't going to come over New Orleans in terms of making their decisions. And I thought that was faulty reasoning. I think most meteorologists think that was faulty reasoning.
Well, there was an army behind them, from Weather Twitter that came out to protect, and defend the National Hurricane Center. Look, this was as good as a hurricane track forecast and intensity forecast too. I think they were predicting rapid intensification when this thing was a tropical depression. I mean, it's at the top of what the science will allow. So to say that the forecast was misleading, it doesn't track. This was an incredible forecast. Now, the problem with the tweet is the ownership and passing the buck onto a bad forecast. It was not a bad forecast. It was an excellent forecast. So you can't say what they did or didn't do prep-wise was right or wrong. I'm glad I'm not in the position to make those calls because I'm sure that it's a really difficult thing to try to plan out how to react to a hurricane threat. But the forecast itself is really good. So if they misunderstood that, or I'll give them the benefit of the doubt, there's a chance that there was somebody that runs a social media account and what got posted to Twitter wasn't really what was conveyed to the person that was typing it by the emergency managers from the university. That's a possibility. It's a
possibility, yeah. We can hope that's the situation.
Yeah.
But the main thing is you don't blame the forecasters anyway. Even if the center ran outside of the cone and ran right over New Orleans. Well, it goes outside the cone a third of the time.
Sure.
So any plan that doesn't allow for a pretty significant hit when you have a Category 4 hurricane forecast to come up to the coast, and you're only about, what is New Orleans, about 60 miles inland or something like that, 60 or 80 miles inland. So, you know, you have to allow for a significant hurricane hit in that situation anyway in your planning. But I think you said the right thing, that it's very possible that whatever decisions they made and where they put the students that stayed in New Orleans, they didn't all stay. A number of them went ahead and evacuated New Orleans on their own and went back home or went somewhere else. But for the ones that did stay, maybe they made all the right plans for them and did the right thing. I don't know. It's too complex a problem, and it's not for us to judge that, I don't think. But you know, you got to own your decisions, and to deflect somehow, oh, the forecast wasn't exactly right or misled us or whatever it was, that was inappropriate, I thought. So anyway, I talked about that this morning in the newsletter. There's going to be a lot to learn from that storm, because even while it was happening, I wasn't sure exactly whether it was evolving in a good way or a bad way for the people in Louisiana when it had two eye walls. Remember this big eye wall? So it was going through this eye wall replacement cycle, which is a normal thing. The inner eye wall shrinks, gets smaller, storm gets stronger as it does that, like a figure skater bringing in the arms, and then an outer eye wall forms, and if there's enough time over the water, the inner one dies out and the outer one contracts in. So it weakens in terms of top winds, the winds expand farther out from the center, and then the eye wall contracts back in and the storm can re-strengthen. So that's what happened in Hurricane Andrew. It hit the Bahamas at maximum intensity. Over the Bahamas, it shed the eye wall, a wider one formed, it weakened, and then as it was coming ashore in South Dade, it was intensifying, and then it ran over the Gulf Stream, and that gave it even extra energy to re-intensify to more or less maximum strength. So all that was sort of normal, except that Ida ran out of real estate in terms of ocean real estate and ran over the land and kind of got caught in midstream of having two eye walls. And they both seemed pretty robust. You know, the inner one really looked pretty strong. So I don't know, we need to get somebody on here that knows more about eye walls than I do to explain whether that was, you know, did that spread the energy out somehow, or did that make it worse, or did that make it less powerful somehow? I don't know. Or maybe it, you know, didn't have a big effect, and the outer eye wall kind of essentially was a strong outer band. I don't know.
Yeah, well, it looked like when that outer eye wall grazed the west side, I don't know if it was the outer eye wall or the primary rain band, the one that was closest to it, but it looked like the outer eye wall had expanded, and then that's what got Laplace, that's what got that storm surge off Lake Pontchartrain. That may have been what clipped the west side of New Orleans. And typically, from what I understand, which I'm no eye wall expert either, when you do get that, the storm damage increases when you have the broadening of the storm, because the wind field's longer or wider, thus more people are going to experience those winds, and generally that means more damage from the storm compared to if it were really concentrated over one area. But the timing of it, like you're talking about, going, you know, it was going over the marshes kind of as this was happening, and there's still plenty of juice for the storm to tap into while it's doing that, even though it's inland, and maintained a lot of its strength. It didn't drop drastically, and now you've got two areas of really intense winds within those eye walls.
Well, so, but I think, though, that the outer eye wall was weaker, which would normally be, right? It's a larger radius. I think that the peak winds that they were analyzing were part of the inner eye wall. So I don't know, but your point is exactly right. When that storms are much more damaging when they're bigger because they're more expansive. Not that you don't do tremendous damage, it's more like a tornado, like a Hurricane Andrew was relatively small. But when they're big, they move more water and they affect more people, like Wilma. Wilma was a giant piece of an eye wall that came over South Florida that extended from south of downtown Miami all the way into Palm Beach County. So you had this, huge, which became almost straight line, right? If you take a circle and you make it big enough, then there's not much arc left to turn, right? And that was the Wilma situation. It was more or less south to north, going, up I-95 when it got here. So as they get bigger, there is more push behind the water, and you end up with big storm surges there in the west side of Lake Pontchartrain. And they don't, by the way, they don't have levees there to really, in a big way, protect those neighborhoods from significant storm surge over in Laplace. And there's a place there called Frenier Landing. I don't know if you saw Mark Sudduth's kind of amazing storm surge video. He put one of his cameras at Frenier Landing. Frenier, it's just Frenier Landing now. The town of Frenier is gone. But there's a restaurant there and a dock, and you can go fish from there and whatnot. And it's kind of a beautiful place, actually. And anyway, he strapped this storm surge thing there, and you can see the storm surge just raging there into the west side of the lake. Well, there was a town called Frenier, and in 1915, there was a voodoo princess that lived in the town. Do you remember this story? There's a voodoo princess that lived in Frenier, and she had some kind of vision, and she said that there's a big hurricane coming, and I'm going to die, and I'm going to take all of you with me. And so she dies, the big hurricane comes, they're having a funeral, and pretty much everybody dies.
Oh my God!
Yeah,
this is a Hollywood movie.
Yeah. It's a crazy story. So that was the town of Frenier, Louisiana, which was a functioning town, but it was in this extremely vulnerable place on the west side of this huge lake. I mean, it's reminiscent of the 1928 Lake Okeechobee hurricane, where when you have a big body of water like Lake Okeechobee or Lake Pontchartrain, if the wind is coming from the north in Lake Okeechobee or from the east to the west in Lake Pontchartrain, the water is going over the land and it's going to take out whatever is there. But look up the 1915 New Orleans hurricane, and you'll see the story of the voodoo princess of Frenier, Louisiana. It's
I'll certainly do that. Story. Yeah, that's incredible. There's a lot of stats with it too. Ida, it's ties for the 5th strongest landfalling U.S. to contiguous U.S. Storm. So one was 1856, which is the famous Last Island hurricane that obliterated, took that island out. And then the other one was just last year with Laura. It tied with Laura. Do you think, something that's really interesting is some of the actual directly observed measurements that were taken from a ship in Port Fourchon of the winds as the storm came through, and it was right in the eye wall. And I think it was 143 or 149.
Gusts to 172, I think. But remember that on a ship, usually that's a significant elevation. So, they'll bring that down some. So, that lends support to the fact that it was a Category 4 hurricane. If the gusts were right at 172, let's imagine that's the right number, which it probably isn't, because usually on ships they're 100 feet up or something. Big ships are big things, right? So I don't know what the elevation was, but it was something. It would be brought down to be standard elevation, which is 10 meters, 33 feet. So. But even if that's right, the gust factor is in the 25 to 40% range. So this is kind of a marine, so maybe it's closer to 20%. Whatever it is, when you take that off to get to sustained winds, you're down in Category 4 range. So I'm sure they'll look at all that and they'll correct all those numbers that are credible, and they'll end up with what they think was the right number. But they had so many airplanes in there, hurricane hunters and whatnot, measuring it, that I'm betting they stay with 150 at landfall. Yeah. And the Last Island hurricane, we say Last Island in English, it's a French place, so they don't, it's called Ile Dernier. If you look on the map, Ile Dernier is still there, but it's all broken up into all little islands because that hurricane wiped out that island that was kind of a resort island on that same barrier island there where Grand Isle is. And Grand Isle, of course, got mauled in Ida. It'll be interesting to see what happens with Grand Isle, because that's a pretty big place, pretty big functioning community down there. It'll be interesting to see, it depends on the insurance situation and whether people can build back. I don't know.
And the port too, this Port Fourchon that took the worst of it is a critical port.
Yes, it
and
is.
There is, they service nearly all of the oil that comes out of the Gulf of Mexico gets serviced by this port. And then a bunch of the grain from the Midwest too, when it goes to market, it passes through this port. So I'd never heard of Port Fourchon. I wasn't familiar with it, but when it hit, I'm like, what is this port? And did some research, and this is a big deal. Not to mention, the economic impacts with that, but the ecological too, because this is where a big chunk of the petrochemical industry is, and there's a bunch of toxic and oily products that are there. And what's the fallout from that? It remains to be seen.
Yeah, it does remain to be seen. After Katrina, there was a whole discussion about should we rebuild New Orleans? I mean, New Orleans and most of that area down there is below sea level, so the only way you can have people living there is to build big walls, levees of some kind, or flood walls or something to keep the water out, right? If you live in your house and you look out the backyard and there's a hill there, and on the other side of the hill there's water, and the water is higher than your house, right? So you have to kind of get used to that to live in southeastern Louisiana. So anyway, there was talk about maybe we just move New Orleans to somewhere else. But the fact is that the United States needs New Orleans to be a functioning city, and southeastern Louisiana to be a functioning area, because so much of the commerce that comes out of the middle of the country comes down the Mississippi on those barges in the port of New Orleans, where the ships actually go up the Mississippi River in the port of New Orleans and Port Fourchon and other sort of support for the petrochemical industry. What's going to happen to that in the future, who knows? But just for commerce in general, it really goes through New Orleans, and that's the lifeblood of New Orleans is that shipping industry.
And the port of South Louisiana, which I guess is on the west side of New Orleans, they took the right side of one of the eye walls. So that was a big hit too. Another big port. How bad? Where does this rank in New Orleans hurricane history? How does this compare to anything else? I know that they had higher winds than Katrina.
Katrina was not a windstorm in New Orleans. Katrina was an engineering disaster. Katrina was a hurricane disaster in Mississippi. But if the flood walls had held as they were designed for Katrina, they would have moved past it. They would have cleaned up. It would have been messy for a week. They would have dealt with it, and the city would have continued as it was. So it wasn't that Katrina was, just this horrible, horrible storm that anything, would have wiped out anything that was there. No, the flood walls just weren't installed the way that the engineers that designed them had said they were supposed to be planted at the bottom. So they tilted over. The bottom kind of kicked out when the water got high on it. If the water had just come over, if you think about it, let's say you have a flood wall, like right now, the flood walls there are 23, 25, 28 feet in some places. So let's say the water gets to 30 feet. If the wall stays, you're only getting water over the wall when it's 2 feet higher than the wall. And the wall doesn't stay at 30 feet for long. 30 feet is the maximum storm surge, right? In an extreme kind of Hurricane Katrina kind of scenario, direct hit kind of scenario. So it's a whole different thing if the flood wall stands, if the levee doesn't breach, if you maintain that elevation of the barrier. Yes, you get water over it, but you also have a big pumping system inside to take care of flood water, in theory, if you have power and if you have enough generators and if you have all the things you need. So, that's how the city exists. It's not just like, oh boy, if there's ever a storm that overtops the huge hurricane protection system that's around New Orleans now, post-Katrina, if that ever gets overtopped, then the city is done. No, because it doesn't stay at that super high level very long. As soon as it goes back down, now the water's not coming in anymore. So all that counts is the water that came over the wall during that extreme period.
Sure, but my question is, compared to are there any other wind events, any other hurricanes that have been in recent memory that kind of match the wind event that was brought on by Ida in the city of New Orleans?
Well, so the big hurricanes in New Orleans, the last big windstorm was Hurricane Betsy in 1965. And my sense is, I don't have the stats for me, but I think it was about this kind of a wind event. The Betsy situation was they did not have the hurricane protection on the east side. The flood wall failed in the lower Ninth Ward. The city flooded. If you look at the Hurricane Betsy pictures, it looks just like Katrina, except they're in black and white, and the cars are old. It's the same flood, the same scenario, and the flood walls that failed in Katrina were built as a result of Hurricane Betsy. In 1947, the Fort Lauderdale hurricane went on to being the New Orleans hurricane, and it was a significant windstorm. Again, until we know exactly what they think the winds were in New Orleans, I'm not sure which would be more, but it was on that same order. Before that, it was 1915. It was the Voodoo Princess New Orleans hurricane that was the big, monumental storm. And they had, in the 19th century, they had a number of storms there. But, the city has existed for a long, long time, and they've had some big floods, but they haven't had, big direct hit, smashing storms like the great Miami hurricane did to South Florida in 1926. In large measure, I think, because they're inland, right? It's more like Orlando, right? Orlando can get a lot of damage, but it's going to be tempered some by the fact that it has to go over land to get to Orlando.
Sure. Okay. But still the worst wind event in 50 some odd years, 50, 55 years.
Yeah. Oh, yeah. And it's going to be, I bet it's comparable to Betsy and 47. I don't know. And I don't know. I'd like to see what the estimates are of those past big hurricanes, but those are the big hurricanes in the 20th century to hit New Orleans. Okay, so there's going to be a lot more to talk about with Ida. I'm sure we'll be talking about it here the rest of the year on the podcast as we get more information. So let's talk now with Dean Ronnie Avissar from the Rosenstiel School at the University of Miami. Hi, Ronnie. Welcome to the podcast.
Thank you. A pleasure to be here.
So you've been at the University of Miami, 11 or 12 years now, and from the outside, it feels like a dean is an administrator that spends a lot of time doing things other than science. But back when you were kind of a regular professor or a researcher, what was your focus and what were you interested in?
So, first of all, you are absolutely correct. Being a dean involves a lot of work that is not directly connected to the science. In fact, the main part of my job is to make sure that the school progresses. So, if anything, I am trying to facilitate our faculty that are the true top scientists in the world to make their job a little bit easier. I'm not promising that I can always do that and that it always works, but certainly the goal is to make the facilities better so that they can do a better research and advance the science and the teaching part of the school. So you're absolutely correct. Me personally, I still do a little bit of research, but you're right, I do not have a lot of time. And the main activity that I did when in the good time when I was a true scientist, mostly weather and climate related from a modeling perspective as well as from an observation point of view. So my own background is at the interface between engineering and sciences, and I have worked always partly advancing some engineering projects as well as science. So the way that I have built my reputation as a scientist was mostly working on the effect of deforestation of the Amazon on the regional and global climate. I looked at the effects on how Amazonia being deforested transfer the information to the rest of the planet from a global point of view. And I have developed models. Okay, I was involved, or the latest development that we have made that is, in progress, as always is with numerical models, focuses certainly on the climate aspect, but also on weather, and more recently over the past few years on hurricane predictions. So I'm going to claim that we have a state-of-the-art forecasting hurricane system. It's right now being improved with the data assimilation, which is, as you probably know, kind of a key element in the success of the forecasting. So like everybody else, we are trying to assimilate as much high quality data as we can into the model, but the rest of the model is a very advanced numerical scheme and has all kinds of advances in science that makes it work particularly well, I would argue. In the past, it was exclusively used for global and regional climate, and we have had some successes that other models were unable to achieve. And we believe that using pretty much the same platform, we are going to be able to deliver a much better forecasting system, especially for hurricanes. So that's what I'm focusing on from the modeling point of view. And then, of course, I have also my pet project, which is observations, atmospheric observations that I conduct out of a helicopter observation platform. And that's a kind of a unique platform. It's still very valuable. I'm not arguing that it's going to continue to be very valuable when the drones are more advanced and authorized to fly in the airspace. Right now, because of the FAA restrictions, we can fly small drones at low altitude, but flying a big drone at high altitude is still very, very limited and not broadly available for the scientific community. So flying real aircraft, airplanes and helicopters still present some significant advantage. And we have kind of a unique platform with the helicopter.
We want to talk to you lots more about both of those in just a second. But let's go back to the Amazon because, we heard for many years, and no doubt your research was part of it, about the threat to the entire planet, really, from the deforestation of the Amazon. And there were the fires and the political issues with the farmers in Brazil and the Amazon parts of Brazil. Is there a reason that we haven't heard as much about that in recent times, or is it just that there is so much more to talk about in the world that it's just overshadowed, that particular issue?
Yeah, it comes back to the news occasionally, I would say, when something big is happening in that area. But the truth is that, it's like I would say almost every aspect in science, it goes by waves. And you have the peak of the waves and the bottom of the wave. And depending on the interest of people, I think that the Amazon was really a key element of the science of the climate, especially 10, 20 years ago. And right now, there are so many other issues that are also important. I would say that the problem with the Amazon has not changed, but the focus of the scientific community has evolved, looking, into the more polar regions and the permafrost and other issues that are important. And of course, everything that is associated with the fires and strong, unusual events from a climate point of view have taken most of the news. The Amazon problem remains a problem. The difference, I would say, with the Amazon problem is that unlike a weather event that comes and goes, right, it appears, or even if you take El Nino, right, it comes and it goes. So you can notice a particular year a very significant difference. with the Amazon, it's an ongoing process that is going gradually, constantly, okay? And the impact is also going to be very significant. But unlike the other processes, it's not that we deforest 1 year, you come back next year, you have back the full forest, and then you deforest again the following year. It's constantly going and constantly influencing gradually the climate system. So that's maybe one of the reasons why we don't hear so much about it. But occasionally you hear again about the big fires and big things that are going on. And if you look at the weather events that are happening in the Amazon and the Amazon basin, you still see quite significant anomalies. Okay, which some of them certainly are related to the effect of deforestation. The process has not stopped. It is maybe politically controlled occasionally a little bit better, but like every other countries, there are also political issues related to that, and let's not get into these issues because that becomes a little bit too complicated.
Yeah, it's an interesting point you both raised. I've thought that before. We heard a lot about that while I was in college. Now all the headlines are about the Greenland ice sheet and the anomalously warm temperatures at the poles, and that's most of what you hear about climate change wise, and not as much about the Amazon rainforest. Is a slow process there. I think you answered this, Dr. Avissar, but getting back to your current role, what you're doing now, what is the role of the dean at a prominent meteorology and oceanography school like the University of Miami? You say it's making sure that you have the best scientists in the world and that they have the facilities and resources necessary to do their job well?
I would say that sums it up. In other words, I mean, from a practical point of view, the dean is making or is responsible for all the decisions that are happening in the research, education, and outreach component of the schools. Now, in order to conduct research and education, obviously we need to attract the top scientists and the top faculty to our school. So a big component of the job has to do with recruitment and recruitment of talent, certainly. And then, the improvement of the facilities. All that is happening at a private institution, but certainly at the private institutions, but also at state institutions is happening through fundraising. So a big component of the job is also fundraising for the school. At the end of the day, right, a private school is a private business. I mean, we are in the noble mission of educating the next generation of citizens and the next generation of scientists. It's a beautiful job, very exciting, and we are all enthusiastic about it. But at the end of the day, we also need the money, okay, to be able to get the best instrumentation so that our scientists, okay, can do the best possible research. And building labs, building technologies, purchasing technologies, having the capability of bringing graduate students and scientists, all that demands a large amount of money. And so a big component of my job is in fact connected to fundraising. And then obviously trying to develop the income resources for the school. Spending them is easy. I have, a list. I have a long list of projects that I need to improve, and a lot of the facilities and new constructions. We just completed an unusual, I would say, but a spectacular pool for teaching diving. Okay, so it's all those facilities require a tremendous amount of money, and so it's not only you need to be able as a dean, you need to lead and provide ideas of what the future is going to be and try to convince the faculty and work in fact with the faculty on identifying what is coming next. And by next it can be next year, but it can be also 5 years, 10 years, and sometimes 20 years in the future, because what we do today is going, in fact, to affect the school for the next 20 years. So it's extremely important to take the time sometime to pause from the daily routine of fundraising and running the operation and managing the staff and the people that we need to manage to support our activity, and stop occasionally and think about, okay, where do we need to be 10 and 20 years down the road? So, to summarize, the job of the dean, I would say it's a mix of certainly of management, okay, a mix of figuring out what is going to be coming in the future, and not to a small extent, also, convincing people that we are an institution worth investing in.
Yeah, it's a remarkable and incredible responsibility, I'm sure. You mentioned management. Management requires experience, and I was laughing with Bryan about this because Bryan's a busy guy, no doubt. But I looked up your CV, and all the chairs and committees and responsibilities and projects that you have been involved with throughout your life is remarkable. I don't know how you've slept in your life. It's incredible. But so, did you aspire to be in management, so to speak, or were you just good at it? Did it come naturally to you? How did you end up on that path?
So, I think that anybody that starts a career as a scientist is not thinking, okay, or at least certainly in my case, I always, especially as a young faculty, to me sounded like, okay, that's the worst future, okay, that I can think for myself, is to move into the administration. I think that there is an evolution in the profession, and you eventually, end up doing what you have, one way or the other, more talent for doing. It's unlikely that, especially, when you are a tenured faculty at a university, it's a difficult landmark to achieve, but when you are there, it's a convenient position to be in. So you have obviously you do have responsibilities and you do have duties, and it's not a simple job. But, one of the advantages is that you have the luxury of designing your career a little bit better when you are tenured faculty. So as a tenured faculty, I started my career at Rutgers, and then I was at Duke. I never envisioned, certainly after being at Duke, that I would move on to become a dean at another institution. But the opportunity came up, and I thought hard about it, about my own contribution to the science. And to be fair and honest, I thought I am going to be able to continue doing more research than I was in fact able to do over the past 10, 12 years. But I certainly do not have hard feelings. It's a different aspect of the job. To take instead of thinking just about what you do and your own contribution, there is a lot of satisfaction in facilitating, the environment for my colleagues to do the best that they can, and developing a new programs, and certainly attracting the top and the brightest students, and faculty to an institution, brings a lot of reward. And in my case, I kind of. I would not say that it comes easily, but it comes somewhat naturally. I'm not doing a particular effort to manage. It's just coming. It's just coming as is, and I am sure that you can ask a few faculty in my school, and they will tell you that I am a horrible manager. But it's the beauty of academia, right? Anybody can express her or his opinion freely and frankly without retribution. No, but seriously, I believe that I have skills in running an organization. I certainly enjoy it. And so that came against, publishing maybe more papers, and I guess that at some point I made the balance, and I have reached peace, I would say, in my decision of moving more into the administrative part because of the reward that brings. And to be also honest, because I have so little time to invest in science, I have the luxury to focus on exactly what I am interested in versus having a big lab with a lot of projects where some of them are super interesting and others are more, to run the lab. So I have that luxury, okay, to be able to focus on the two projects that I am really very, very interested in. And so that's where we stand. That's where I stand.
So I know you're from France and you did your university work in Israel. Did you always have in your mind you wanted to come to the U.S., or did you come here because we have hurricanes?
I didn't come to. I never thought that I would be working on a hurricane. To be completely honest, I started my career, as you pointed out, in Israel. I grew up in France, but after high school, I moved to Israel. And I got into the field, just by accident, I would say. I started my career in agronomy, believe it or not, and I was in my last year of agronomy. I had to design irrigation system. And it turns out, especially in a country like Israel, that evapotranspiration is kind of a key element, okay, of an irrigation system. And through that, I got interested in micrometeorology and turbulence. And from there, I went into my graduate school also at a time where computers started to bloom. So, we are talking about the 70s, right? And the concept of simulations interested me a lot. And I developed for my master's degree a model that is capable of simulating the micrometeorology of a greenhouse. And then from there, I moved into mesoscale meteorology for my PhD. And the global aspect, came a little bit later. In mesoscale meteorology, I focused on land-atmosphere interactions. I had a lot of knowledge about the land, about soils and biology through my agronomy background. And I simulated the processes that I introduced into weather and climate system. So at the time, again, there was not much of that activity going on. It was not perceived as being an important factor, but I kind of built, a career on that and started by developing, again, mostly land components of weather and climate models. And the focus on mesoscale meteorology was particularly interesting at the time, and then it expanded to the global scale. And certainly with the Amazon project, I was able to reconcile everything that I had learned, both from a biology point of view, a soil point of view, regional, turbulence, mesoscale, and global scales.
So it sounds like the irrigation project maybe was the beginning or one of your first interface between meteorology and engineering projects, right? So
Absolutely.
I guess the when you really get down to thinking about it, and we don't really think about it this way, but everything has to be measured so that you understand the initial state of the atmosphere or whatever it is that you're dealing with, right? Is that what you focus on? Is thinking about how you can use your engineering expertise to better measure the natural world? Is that a reasonable way to think about it?
Yeah, I would say absolutely. The engineering background has allowed and helped me develop new ways of observing the environment. Again, I mean broadly defined the environment, right? I focus mostly on the atmosphere. I don't measure, certainly not currently, anything else. But definitely, combining the desire of developing new measurement techniques and new platforms and new instrumentations, plus the scientific interest of understanding what is really going on. I think that what has been particularly rewarding from my point of view is that, as I mentioned, I started from modeling, which is kind of a theory, right? You take some concepts and certainly you can evolve with that up to a certain point, and then it's at that limit, right? You figure out that the only way you are going to be able to go to the next step is by looking into it and try to figure out what is going on. So that's kind of the evolution of my career. I have gone from modeling to more observations, back to modeling, back to observations. And, as probably a lot of the scientists that I know have reached a similar conclusion, at the end of the day, it seems to me that certainly for weather forecasting, okay, we are at a crossroad where unless we are capable of literally moving to the next phase in modeling, which is going to be resolved not only from a numerical point of view but from a mathematical point of view, the Navier-Stokes equations. We are still resolving them numerically because of the limitations that we have from an analytical point of view. So there are a lot of efforts that could be conducted from a theoretical point of view and mathematical point of view. But that's honestly beyond my capability, and certainly at this point of my career. So I've reached the conclusion that the merging of observations and numerical techniques is certainly going to help us in the next coming years, trying to do a better job than we do today. Not that we are doing a horrible job, but certainly we can improve. Okay, I think it's a very feasible to provide a much more accurate 3-day or even 5-day forecast, certainly of the track of the hurricane. I mean, there is room for improvement, and I think that is going to come with a better merging of observations and observation techniques that we assimilate in state-of-the-art numerical models. So that's where we stand, and it's where I am stuck with in my career right now. Really trying to solve that issue. And the hurricane problem is a fascinating one, but it's also, I would say, a gateway to multiple other issues that we are trying to solve in the earth sciences. So this one is very visible and it's very powerful, as we all know. So I think it's a good example to use and focus on. But so that's what I am, trying to progress. And I have my own observation techniques with the helicopter that I think are going to provide some insights on hurricane intensity, and that will help us assimilate better data so that we can do better forecasting. But obviously, efforts that are being conducted right now with constellations of microsatellites and these type of activities as I think that's going to provide a huge progress for us. Okay.
Yeah, so the interface between the observations and the models, right in the middle of that is that data assimilation problem you talked about. And Luke, I think, was going to ask you about your hurricane model, Luke.
Yeah, that's with all the talk of modeling, with your specific project, the OLAM, the Ocean Land Atmosphere Model. Tell us about that. What is that?
So the Ocean Land Atmosphere Model is, now it is not anymore a new product. We started to develop it about 20 years ago. Well, maybe even more than that, 20, 25 years ago. It started from a simple desire to expand properties that we have in mesoscale models, okay, being, non-hydrostatic. Again, remember, 25 years ago, the thoughts were very different for global models. Try to expand the mesoscale models that we had into a global scale. And in the process of doing that, we realized that we are way better off starting from scratch and, just redesign completely a model that is better adapted for global problem, especially with in the background, the capability to increase resolution in places where we believe that we had a lot of interest. So the capability of having a global grid that can intensify, if you prefer, the resolution at a specific location on the planet was the goal. And we came up originally with a global grid that had, triangular shape that translated eventually into an hexagonal shape. And all that, again, I'm talking about 20 something years ago. Eventually, the big advantage of the model that we have is that it resolves the full Navier-Stokes equation. So it's not like a typical mesoscale model that is based on perturbation equations. And then it is global and non-hydrostatic. So there is no fundamental assumptions that we need to make on all the process. So it's an interesting simulator because on the one hand, we can do large AD simulations, which is simulations of turbulence at a scale of millimeters, literally in a global grid, right? Going all the way to global processes, of course, at the global scale. So from that point of view, certainly again, 20 years ago or 15 years ago, when we came up with it, it was kind of a novelty. Since then, it has improved tremendously with better precipitation schemes, better radiation scheme, better turbulence schemes, a lot of improvement. Land surface, okay, has improved considerably. Hydrology, so our model is capable of simulating surge, for instance, and and the consequence of a surge and high precipitation on floods. Okay, so all kinds of advantage, if you prefer, that do not happen or are starting to being developed now and are starting to happen in other models that are developed by by NOAA and the National Science Foundations or UCAR. So that's what OLAM is all about. It's a sophisticated simulator that can work at the very, very micro scale in a global grid.
So if I'm just trying to conceptualize it, tell me if I have this right. So it's a weather forecast model. It's coupled land and ocean, and it has an ability where you have a set number of grid spaces that are in the shapes of hexagons, and you can harness the computer and move these hexagons into really small, tightly packed clusters over some spots of the globe, and then maybe they get larger in other parts of the globe that you're not as interested in. So you could, for instance, maybe focus it over the Caribbean if there were a hurricane there. Do I have that right?
You said that much better than I did. You're absolutely correct. So we are putting the computing resources in the phenomenon that we are particularly interested in. So for instance, we have the formation of a hurricane somewhere in the Atlantic. We can start simulate that hurricane at very high resolution. So you take your best camera with the more pixel and you put it right over that hurricane. And for the rest of the planet, you are still simulating the large scale processes, but at a lower resolution, because you are less interested in the details and you are more interested into the big weather features. Okay, there is an interaction, obviously, when you start trying to figure out the track of a hurricane. There is a huge interaction between the large-scale phenomena as well as the micro scale that is developing at the hurricane. So we are capable of simulating that by focusing our computing resources into the micro scale, the high resolution phenomena, while we can put still some computer resources, but much less, on the order of 5 or 10% of the computer resources into the large scale processes that are far away on the other side of the planet.
Okay, a two-part question for you. I did a little research on this, and I found somewhere that this model incorporates gravity waves as a way of forecasting what a hurricane may do. And I had never seen that. It seems like a radically new technology. So that's question one. Question two, if that's true, aside from that, how is this different from the other models that we're all familiar with, the GFS and the HWRF?
There are a lot of the technical aspect of the models that are still under investigation to know as, specific for the hurricane of what is important and what is not important. The issue of the gravity waves is an interesting concept, okay, that we are trying, in fact, not only to model, but we are trying also to monitor and observe and understand better. So that's where, in practice, where the helicopter is coming in, and with the devices that we have installed on it. We still have some work to do into that, and try to understand a little bit better how we manipulate that. In a numerical model, just to, without getting into a lot of details, there are a lot of waves that are generated. Some of them are real physical waves. Some of them are byproduct of simplifications that we are making and assumptions that we are making, or purely numerical techniques that we are using. So the challenge and the interesting part in the research is to figure out how to filter, okay, and how much filtering you put into the different components of the models and into the different components of the waves, okay, that you generate. So there is no, honestly, I do not have a good answer for you right now of what is truly important in the process of what we are looking at. We are focusing on that, obviously. One of my colleagues here at Rosenstiel has been monitoring gravity waves in the past. Dave Nolan, he has observed them, and on a buoy, okay, in the ocean. We have developed the technology to be able to monitor them and measure them on the helicopter. We believe that we are capable of doing that. It's also under development, so there are some frustrations in terms of achieving exactly what we want. But as we speak, we are modernizing the system that we have on the helicopter to be able to monitor them. When we monitor them and we can quantify them, it will be much easier for us eventually to tune our models, okay, for what is important and what is not important. Now, again, the techniques, okay, when you compare a model, okay, to other models, a lot of it has to do, honestly, with that capability. So there are, multiple components that play a game in there. There is the fundamental equations, okay, and from my point of view, using the major part of the fundamental equations is a better approach than using approximations to those fundamental equations. So that's one aspect where, at least theoretically, I am more satisfied with OLAM than I would be with other models. There are numerical techniques, a lot of them, okay, that we use for multiple processes that are relevant to anything happening in the model. Then you have the physics of it, the radiation, the clouds, the parameterizations, as we call them. which is representing what has not been resolved by the pure fundamental equations. How do we combine the multitude of processes that are happening in the real world into a grid, even if it is, a high resolution, it is still, let's say, 1 kilometers or 2 kilometers. There are still a lot of things going on over there at that scale in terms of turbulence and interactions with the microphysics, with the drops of water, ice, snow, whatever it is that you are simulating, and the radiation that is going on with that. So there are a lot of in the parameterization, okay, that is different. So the different models are going to vary in that, systematic approach to looking into the real physics of the system and the approximations that we are doing. One of the aspects that I love about OLAM that can be argued against, the other organizations are working as large teams, and they have a lot of programmers and a lot of physicists and modelers that are getting together, and each one is providing an opinion, and you mix all that knowledge and you come up with a design. In our case, it is a small team that has been working on this project, and we are super consistent, okay, from the micro scale all the way to the large scale, that none of the assumptions that we are making are not consistent one with another. So, when we look into the precipitation in the cloud, from the clouds, and it hit the ground and gets into the hydrology, it's a one continuous line of thinking that is being brought into that model. And we believe that we have an advantage by doing that. A lot of thought has gone into it. We have some interesting results and some successes with this model that other models have not had. So, I think that there is a benefit in the multitude of approaches. But I think, certainly I am very satisfied with the one that we have developed that has been successful for us over the years. And I believe, honestly, that with the improvements that we are going to be making in data simulations, again, thinking about what is coming next and how we can best exploit what is out there, and combining that systematically in a consistent way with our physics and dynamics of the system, I think that we are going to have an edge on that. But hey, let's talk in a couple of years and see what is our forecast versus the rest of the other models.
Well, so I want to ask you about the helicopter, but before we do that, so when are we going to be able to see the output of the OLAM model like we see the outputs of the other models?
So,
and when will it join the family of forecasting?
All right. So, the main disadvantage that we have of not working as a large team is that, to operate a model in an operational way, where you have, today I can provide you a 3 to 5 day forecast that I can put out there, as one of the spaghetti line, right? It requires quite a lot of involvement. Believe it or not, but this year, for the first time, we have been able to do that. So for the first time, we have produced, in fact, 3 days and 5 day forecast with our models. We need computing time that we do not, right now, this year, we were able to manage that, but on the longer term, okay, we need to have access to a big supercomputer that is capable of helping us with that. And I need to be able to obtain the fundamental resources that I need to have at least one person or two people working in an operational way using the model and being able to compare it to others. Okay, so it's a more financial aspect. The resources, it's not nothing to do with the technology. Again, this year we have been able to demonstrate, because I was fortunate enough to get a little bit of money to put somebody full-time on it. So we have been able to do some forecast. And I can tell you that with Fred, okay, for instance, we predicted 3 days ahead of time perfect track and very good intensity. So that was very satisfying. Again, we produced only 3 days, 3-day forecast at the time, but we were really very happy with the product. Again, so that's the main issue, right? To be able to deliver you a product, I need to be able to get a little bit of a support to work on that. And frankly, the area, I mean, the people that could sue, or the agencies that could support us for that, are not necessarily, they would rather put their money into their own product than in our own product. So we have a little bit of that dispute over there, or not dispute, but I understand, we have to understand the challenges. But so I think that, we could be compared now, to other simulators, and we are doing it, and we are comparing ourselves, to other forecasts. I promise you that when I am sending the report, we are still waiting another 2 months or 3 months in this season. But I promise you that when I send the report to the private foundation that supported our research, I'll send you a copy.
Okay,
So
I want to see it.
You can see what we have done. Retrospectively, you can
Sure.
you will have to trust that we are sending you the right thing. But I would be I am optimistic that starting next year, certainly locally, we are not going to be able to diffuse that, on a broad forecast. But certainly locally, I'll be able to send you our output, and you can put it on the side and look and say, let's not advertise too much about it. But if you are happy, then the following year, you'll put it forward.
Great.
And
I can't wait. I can't wait.
Yeah, me neither. I mean, obviously, let's be realistic and practical. There is. I doubt, that any model is going to be 100% successful, because you always have something into the process, that is going to vex, the programmers that have designed those models, and we are learning from that. But under normal circumstances, and I would argue especially when there is a strong interaction, with the mountains of Hispaniola and Cuba, I think that that's where our model, excels, in the interaction with the topography and with the land. We are representing those mountains in a much better way, much better resolution than any other model is doing. So I think that we have a big edge right there. And, I think that our forecasts are going to be doing a better job when that happens. When you have a hurricane that is in the ocean and it's a kind of a simple hurricane to forecast, I think that we are not going to see major differences. But in the cases where it's complicated and there is a lot of interactions with the land, I think that our model will do better.
Yeah,
and
with those, what was the storm that just hit the mountains?
Fred was a big.
Anyway, was it basically a crapshoot on how it was going to what was going to emerge on the other side, right? So,
exactly.
So you do have these variables in the model. First of all, you have to measure the atmosphere. Then you have to take all the data and put it in a way that the model can run it to make a forecast, and then you make the forecast, right? And actually, as I understand it, the measuring of the atmosphere and then assimilating the data into a form the model can take it, those are actually harder tasks. And in terms of the measuring the atmosphere, you have the helicopter as a, I know your pride and joy, because I remember I was there when the helicopter first arrived, and you had designed many interesting monitoring systems on the helicopter. So talk about the helicopter, what you have measured, what you hope to measure, and how you think that's going to make a difference in the information we have going into the models.
So I want to clarify, that the helicopter is a research tool. It's not an operational one, I don't anticipate, certainly not in the near future, taking the data that we are collecting into the helicopter and use that operationally into hurricane forecasting, for instance. Okay, that's not the goal. And honestly, I think that if any direction is going to help us do a better job, that's going to be coming from satellites, because we need a large coverage. We need to understand, what is happening over a larger area and not a single flight or a single observation. It's useful from research perspective. So from
But
a
maybe
research
eventually drones, right? If you learn with with the helicopter that a certain kind of data makes a difference in the future, you could imagine sending a drone out to get that kind of data.
Absolutely. Right? And as you pointed out, eventually having multiple drones well located, at a good distance from a hurricane, monitoring gravity waves could be used, to help in the forecast of the models. We believe that eventually that is going to be providing important information. But at this time, what we are using the helicopter for, again, two types of applications right now, and there are a few others that are in preparation. There is the weather aspect and there is the climate aspect. From the weather aspect, we are in fact engaged right now in monitoring gravity waves that are being emanated from the hurricanes. And we are trying to quantify those gravity waves. By quantifying, I mean we are trying to understand what is their amplitude, what is their wavelength, at which distance from the hurricane. What is, the idea that we have behind it is that is the following. If you intuitively, right, if you take a stone and you throw it in a pond of water and you look at the waves at the surface, intuitively, if you have a small stone, it's going to make a few ripples on the water, and they are going to propagate, a few yards away. If you take a big stone that you throw in the same pond, the waves are going to be much larger, and they are going to propagate further away. So we are using that concept by claiming that the strength of the hurricane could be or should be identifiable and quantifiable by measuring the gravity waves that are emanating from the hurricane. And big waves that are propagating far away will correlate with a strong hurricane, so large intensity, and the small waves are going to be indicating of a smaller intensity.
I hate the word gravity waves, by the way, because I don't think anybody that doesn't study meteorology understands. This has nothing to do with gravity. This is essentially the pond and the stone analogy is a very good one. This is like a disturbance moving through in a wave-like fashion related to some sort of initiating event or initiating circumstance, right?
And
I don't want anybody to get confused about that. We're talking about the kind of gravity waves that people are trying to measure in space that are actually related to gravity, right? This is a different thing.
Very good point. And indeed, I was going to say that be careful not to confuse that with what astronomers are talking about, because that's a very different process. But so that's the best analogy that I can make is with the ripples at the surface of the water. So that's what we are looking at. So right now we have the technology that is allowing us to measure, those disturbances in the atmosphere, which are small vertical disturbances that are emanating from the hurricane. And so our approach right now has been to go to an altitude on the order of 7,000-8,000 feet. And at a distance, we start try to observe them when the hurricane is still at about 1,000 miles, so very, very far away. And we want to do that consistently until the hurricane is only maybe 50 miles away or 100 miles away, as long as it is safe to fly helicopters. We are still trying to figure out what is the best altitude at which we can measure that. It's very clear that closer to the ground surface, there are so many other disturbances that it's probably not a good idea. Very high, it's probably not a good idea neither. So we have kind of, figured out 7, 8, 9,000 right now is where we are putting our best bet, but even that, needs to be confirmed. So we do have sensors, and I invite you to come and see the newest sensors. I mean, literally, I have a graduate student working with me that is right now, closing the box, with the new sensors that just arrived a couple of weeks ago. That we are mounting on the helicopter. And so that's kind of the main project that we had related to weather and hurricane. The same set of sensors with additional one can be used in a climate sense to measure what we call fluxes that are, or the exchanges, if you prefer, of gases and heat between the Earth and the atmosphere. So it can be above land surface, so it can be above the ocean. And in that case, we are making observations in what we call the atmospheric boundary layer, so the lowest level of the atmosphere. And right there, we are trying to measure by a technique which is called eddy correlation technique. We are trying to measure the fluxes of carbon dioxide, heat, and moisture that is coming in and out of the ocean and the land above different types of lands. So that's more of the climate aspect of it. And by the way, we proposed to do the same thing with methane in the highest latitude above permafrost, and the technique should work. And there are instruments that could be adapted on the helicopter that could make those measurements feasible. And so that's a project that we would love to participate in. So that's currently what we are doing with the helicopter. Independently of that, we have some remote sensing observations that we are going to start doing with the helicopter. So one under development project is mounting a SAR, a synthetic aperture radar, on the helicopter. And that will allow us again to, identify waves and quantify them above the oceans, all kinds of land processes as well that we can identify with this type of technologies. This is not my field, my own field of expertise. That's something that I am going to be interacting with some experts at Rosenstiel. And then, as you might have heard, we just recruited the new director for a center that we recently funded at the school, which is called the Aircraft Center for Earth Studies. The helicopter is going to be a small component of that because the focus is going to be on drones. And we recruited a director for that center that has all kinds of ideas on how to combine drones and helicopters together to make some better observation systems. Keep in mind that right now, one of the big limits of use of the drone is the line of sight of the drones, right? That's why you have to remain close by when you launch a drone and at a low altitude, because there is a fear that they can get out of control. If you fly a helicopter, right, let's say at 7, 8, 9,000 feet, and you look at it from above and you have a fleet of drones flying with the helicopter, you do not have the problems of line of sight because you are above them or together with them, and that problem of line of sight. So that simplifies a lot the communication, and through that we hope to be able to achieve also some good multiple observations capabilities. So a lot to pay attention to in the near future. As soon as that director joins, we'll introduce him to you. His name is still confidential because he has still not announced that he's leaving his current position. but we are really looking forward to easy interactions to work with us. And what we started to mention at the beginning, the helicopter again is a good platform right now and for the next 5-7 years. In the future, I also believe that will be replaced by drones and sophisticated drones. So be it, that's part of the evolution of the technologies that we are using.
So two really big endeavors that you have going on there with the HOP project and the chopper and OLAM. But tell us about some of the other big initiatives going on at Rasmus. I would assume that climate research is an increasing part of most new research projects. Is that true?
First of all, climate research has always been a huge endeavor at Rosenstiel. So we have a reputation, we have experts in so many areas, okay, whether you look at the biology, the chemistry, the physics of the climate system, we have not only one expert, but we have multiple experts that are working on multiple projects with multiple organizations. So it's a big endeavor that we have at Rosenstiel. And I would argue that one way or the other, probably the vast majority of the faculty that we have a foot in the climate research. Okay, it might not be directly, but indirectly, okay, is connected. But certainly purely climate. So in our department of oceanography, our department of atmospheric science, our department of biology, our department of geology, and our Department of Marine Affairs, which is recently renamed Environmental Science and Policy, we do have several experts, okay, in the field of climate. If you ask me to say everything that we are doing, it will take me honestly about a week non-interruption to speak, okay, about that. We have currently, I am guessing, and probably conservatively guessing, we have on the order of 100 projects going on. And I'm talking about research funded by federal grants. Okay, so top ranked project nationally that are going on. Probably the most powerful one is the collaborative agreement that we have with NOAA, okay, in our Center for Interdisciplinary Research that we have with NOAA, that is in fact a focus on climate, weather, and the fisheries. And somehow, a lot of the projects that are going on over there are strongly related to the climate system. So a lot of interactions going on with other organizations, many projects. Again, you can look at everything that is going on from the biology point of view, the coral reef point of view, and the bleaching of the coral reef and its relation to acidification and raise of temperature. Again, all that is somewhat, maybe in terms of the research, not directly connected to the climate system, but very connected to it through the indirect effect of acidification and temperature changes, right? To the projects that are what one could call the pure climate research, like the work that Dr. Kurtman is doing in trying to assess seasonal climate effect on the weathers, and the work that Dr. Clement is doing on her paleoclimate work, understanding better the interactions between the oceans and the atmosphere on the long time scales. You name it, a lot of observations going on in the ocean, in the atmosphere, in the geological record, okay? Plus certainly the policy aspect, the human aspect of it. So, honestly, we could talk about the climate, much more interesting projects than I do, to be completely honest, that are going on at the school related to climate and fisheries in general. So.
So before we let you go, because I know you have, I know you, and I know there are just an amazing number of really interesting ideas and projects going on. But before we let you go, I want you to talk about the changes, the physical changes in Erasmus and that have happened in your time and what you have planned to the physical campus there. I mean, I've been coming to Virginia Key to that campus for decades, and it has been remarkably altered in your time there. How has it changed, and what are your plans?
So over the past decade, we have indeed been able to achieve a few changes on the campus. Modernization of facilities that badly needed to be improved. So we developed a new seawater complex, okay, that includes both the biology and the physics, including a hurricane simulator capable of simulating a hurricane force 5, where we have both the water tank and the wind, okay, blowing above the water tank. So it's kind of a unique capability that is included in this complex. But we have also the building has running seawater through it. So all the labs have the capability to use seawater, and that allows us to conduct research on every animal that requires seawater. So that's that was a big project that took a lot of resources and a lot of effort that we completed, believe it or not. I believe that we inaugurated it in 2014 or 15. So that's already an old project. And then I mentioned at the beginning of the interview, we recently completed a diving center that includes a large training diving pool. So it's a different pool because it is very deep, 15 feet all over the pool. And that allows us to train the next generation of scientists as well as students, okay, that are going to go and work in all the organizations, being able to provide a good education there. We have improved tremendously our aquaculture center. That's another part of the school where we have a lot of expertise and needed to make improvements of the facilities. And right now we are in the process of designing a new building that is going to allow us to host the NOAA fisheries on our campus. So we are going to release some of the space that we have right now in one of our buildings, modernize it, host our colleagues. We want, I think that it's not a secret that NOAA is interested to be more embedded inside campuses. It's a good model that is working well for their research. And obviously, having them across the causeway has been a great advantage for us. We love that interaction that we have with NOAA. It's a big component of what we do. We love the research that we do for NOAA, and we certainly want to have them even closer to us by having them on our campus. So we are modernizing again the campus to be able to host them on our campus. So yeah, a lot of changes that are very visible on campus, but a lot of changes also that are not so visible. We invested a total of about $30 million in modernizations of the different labs and different facilities, including our cafeteria, which is a spectacular place to come and have lunch and come, anytime that you want. We have in the non-COVID era, unfortunately, that has affected us negatively. We have the nicest bar in Miami, okay, that is led by the students and organized by the students, and it's a great place to meet and to get to know the school. We rebuild the amphitheater also that we have. I mean, it's a lot that is going on constantly. Every year we invest several $1 million in improving the campus and the facilities. So indeed, when I arrived, facilities was a top priority, and I fundraised mostly to improve our facilities, to be able to improve the quality of the research that we do. And right now, the current fundraising campaign is focusing on recognitions of the talent that we have, so through scholarships and through professorships. One of the great way to attract talent is by offering what we call an endowed professorships. It's a title. It gives a little bit of discretionary funds, which is always great to get because, here and there it can help paying for a graduate students or renovating a little bit of a lab or taking a trip that otherwise you would not have been able to take and try new ideas that are typically not supported by federal grants. So, it's a prestigious title to have. And honestly, we do not have enough, at Rosenstiel. So a big part of my fundraising effort right now is to create new centers that are going to be hopefully leader centers in the future. And as I pointed out, we are trying to look 5, 10, 20 years in the future. And each one of those centers has endowed professorships as well as endowed scholarships to attract the top students. The other part that we are doing, we created new program. If you knew Rosenstiel all the time, it was focused totally on support from federal agencies, which is still great and in fact better than ever, but it's too small to be able to carry the type of enterprise that we want to have at a university, at a private research university. Obviously, we want to do top science with top scientists, but our mission has a big component of education. And certainly to me personally, I am very committed and motivated to do that. I have a lot of passion for education and provide what I believe is going to be a game changing in undergrad education. So we are transforming the current model, which is what I call the classroom-based model, where students, go into a classroom, have the professor on the stage giving their 1 hour and 10 minutes talk, occasionally, have a private conversation with a student, but still, you go to a private organization, you have all those great people that you see in the class, but that's not a true interaction. So we are kind of eliminating that model, and we are changing the way that we teach by taking the kids in the lab, working on research project, real research, not something that we know the result because we have done it 20 times in the past, but tackle a real research project. And through that research project, we teach them how to identify issues, how to resolve those, or how to provide information, how to communicate those results, how to analyze the data, kind of the entire process of the science, but forcing them, to get the information that they need, by picking up the information on the web or in the books, and sometime in the classroom as well. So it's a big project, that we are all involved in, that is going to modernize our teaching way and the way that our students are going to be educated. So.
It's amazing, and congratulations on how far you've come, and it's wonderful to hear about all the plans to take the university and Rosenstiel to another level. You run a great school and have an amazing array of great scientists. We talk to them all the time and are constantly, literally amazed by the ideas from the University of Miami people. Thanks so much, Ronnie. It's really good to see you again.
And it has been a privilege for me to have the opportunity to serve as the dean of this school. And I greatly appreciate also, the relation that we have developed over the years. And when you were still a young kid working for the Weather Channel, right?
Yeah, right. That's right.
And so that's very true. And I really appreciate the interactions and the discussions that we have had over the years. It's a fantastic, and let's continue doing that.
Yes. All right, Ronnie, thank you. And you be well.
Thank you, Brian. Thank you, Luke. I really appreciate the opportunity to speak with you guys.
Dr. Ronnie Avissar at the Rosenstiel School of Marine and Atmospheric Science at the University of Miami. So, Luke, it's interesting from our perspective to hear about all the kind of behind the scenes research and thinking and planning and trying to get at the edges of the hurricane problem to just make it that much better and that much better. So try and find a string to pull on that will make a difference in our understanding.
It's a couple things really stood out to me. One is the helicopter program and the idea of using a new way to measure the intensity of a storm. When you take a radical new technology and try to see if this works, which it sounds like it might, and these perturbations, these little ripples that go through the atmosphere to determine the intensity of a hurricane, I love that. We know how important it is to know the current intensity of the storm, to put into the models to get a better forecast. That's the whole goal, right? Get a better forecast. So try something new and different that nobody else is doing. Is radically new, is fascinating to me. And then on top of it too, I imagine the efficiency that a private institution like the University of Miami has allows them to get the ball rolling more quickly, probably more cheaply than government institutions. So it's really encouraging to see all that's going on there, which is a vast amount of work and research.
It is the beauty of the American system, actually, is that we do have this merging of government efforts and the government research and so forth, but we also have academia at a private level. As Dean Avasar said, they're nimble. They're a small team. They make a decision and then they go do it. You can imagine working in a government-funded operation that, you probably have to talk a few layers up before you change direction, for example, and pull on a new string. So anyway, it was great to talk to Ronnie. So be sure you subscribe to our podcast on your Apple or Android app so you get notified when the next podcast is online. Or, of course, if you follow me at B Norcross, at B Norcross, or at B Norcross WPLG, either one. On Twitter, I'll put the notification right on there. You'll see it. Or on Facebook as well. If you follow me on Facebook, you'll get the notification as well when there's a new podcast. And you can watch it in audio and video on local10.com, or again on Facebook. I'll go ahead and give you a link there that you can watch it either audio or audio and video. So until next time, for Luke Doris, I'm Bryan Norcross. Stay safe, be well, be sure you're vaccinated. It's more important than ever, and we'll see you next week.